Today we're going to talk about the combined gas law. So far, we've already talked about 3 of the gas laws. Now, the combined gas law will have some variables that will look very familiar from the other gas laws we've learned about. On this slide, I have Boyle's law, which represents the relationship between pressure and volume. So we have P1 V1 equals P2 V2, or the first pressure and volume are equal to the second pressure and volume multiplied together. Then we have Charles's law, where we have the volume and our temperature, and it's V1 over T1, so divided, equals V2 over T2, so also divided. Then we have Gay-Lussac's law, which is pressure and temperature's relationship. We have P1 over T1 equals P2 over T2. Now the combined gas law looks really familiar. This is all of these combined. These are where we're looking at multiple different changes, where we have pressure, volume, and temperature, and we're looking at a change in our gas. So let's look at a practice problem that talks about the combined gas law. Here we have a gas that's contained in a 5.0 liter container at a temperature of 300 Kelvin and a pressure of 2.0 atmosphere. What will be the pressure of the gas if the volume is changed to 10 liters and the temperature is increased to 350 Kelvin? We're going to use our combined gas law, which I'll write right here. It's P1 V1 over T1 equals P2 V2 over T2. Now, we need to figure out what our pressure, volume, and temperature variables are. So let's start at the beginning of this question. A gas is contained in a 5-liter container. Now we know that liter is going to be a variable for volume. Liter is going to be a unit for volume. Then we have temperature of 300 Kelvin. Well, the question tells us that that is our temperature. And a pressure of 2.0 atmosphere. This is our pressure. Now it says, what will be the pressure of the gas if the volume is changed to 10.0 liters, so another volume, and the temperature is increased to 350 Kelvin, another temperature. So I'm going to make the 2.0 atmospheres our P1, our 5.0 liters V1, our 300 Kelvin T1, then we have our V2 and T2, and we are solving for P2. Now let's plug everything in here. We have 2.0 ATM times, in this case, 5.0 liters over 300 Kelvin equals, and we are solving for P2, so I'm going to put in P as the variable that we're solving for. Our V2 is 10.0 liters, and that is over 350 Kelvin. So now what we're going to do is we are going to solve for the pressure. So we can solve algebraically for the pressure here and see what we get for our P. To solve this algebraically, you can either cross multiply or you could multiply both sides by 350 Kelvin and then divide both sides by 10 liters. It's up to you how you would solve that. If you would like to pause and try to solve it yourself, now would be the time to pause because I'm about to write up the answer for this one. The pressure in this case will be 1.2 ATM. Now, our liters cancel out and our Kelvin cancels out when we do this math algebraically. For the reason I rounded it to 1.2, all of these numbers have 2 significant figures or more, but 2 is our lowest number of significant figures, so this one will be rounded to 2 significant figures. In the second practice question I've written, we have a balloon now, and a balloon is filled with gas at 1 atmosphere pressure and a temperature of 273 Kelvin. The balloon is then moved to a location where the pressure is 0.50 atmosphere and the temperature is 323 Kelvin. What will be the final volume of the balloon if the initial volume is 2.0 liters? Now, just like before, we're going to figure out what our variables are. Now, some of these tell us right off the bat they tell us that in this case, this is pressure. Let me actually change my pen color here. This is pressure. Then we have, it tells us our temperature, so that's T. And in this case, it tells us our initial volume way down here at 2.0 liters, so this is our volume. Now, we have another pressure variable right here, 0.50 atmosphere. This is the pressure, and we have another temperature right here. Now, we're going to have to be very careful with which one we're setting as P1, P2, T1, T2, V1, V2. We know that we're solving for a volume, but let's look through here. So I'm going to set this first pressure that we see to P1. Now, the temperature at that pressure is 273 Kelvin, so this will be P1 as well. Our initial volume is way down at the end of the question. This is our V1 right here. That makes this P2 and this T2. Now, our combined gas law is P1 V1 over T1 equals P2 V2 over T2. Let me just make that 2 look a little bit more like a 2. There we go. Okay, let's plug everything in. So just like before, we have 1.0 ATM. And this is at 2.0 liters, that's that volume, over, and RT1 is 273 Kelvin. This is equal to, and I might have to erase our equation here. Should have moved this over a bit more. I'm just going to erase this though. Our P2, which is 0.50 ATM. We don't know the volume, so that's what we're solving for. And we're going to put that over 323 Kelvin. Now, I talked about some of the steps you do to solve algebraically. If you wanted to do cross multiplication, what we would get is we would cross multiply, and I'll do this in a different color. We'd cross multiply here, and then cross multiply here, and then we would solve algebraically for this. So what we would end up getting is 0.50 ATM times 273 Kelvin times V equals 1.0 ATM times 2.0 liters times 323 Kelvin. To get V on a side by itself, we're going to divide both sides by this 0.50 ATM and 273 Kelvin. We're actually dividing this whole thing by that, and we would get 0.5 ATM over here. I'm sorry, this is 0.50 ATM and 273 Kelvin. Now, over here, these cancel out because we've divided by the same number, so we have V on a side by itself. But before we calculate this, I'm going to show how the units cancel out. Our ATM are on the top and bottom, so our atmosphere on the top and bottom, those cancel out. Our Kelvin is on the top and bottom, and those cancel out, and I'll do a different color here. This liters is the only unit left. So in this case, to get our volume, we're going to need to solve for this. So what we're going to do is we are going to take 1 times 2 times 323 divided by 0.5 divided by 273. In this case, if you want to pause to try to calculate it, now would be the time, because I'm going to write the number up here. What you should get with our two significant figures, so our lowest number of significant figures is 2 from all of our measured numbers, we get 4.7 liters. So that's our answer for this one. This is how you do the combined gas law. If you have any questions, please let me know.